Welcome back to UBG Bytes. We're tearing into a fascinating source document today, a research paper introducing a new benchmark for evaluating AI agents in video games. It's called ORAC.
That's right. And ORAC, well, it's presented as a really foundational benchmark. It's
Hmm.
specifically designed for training and evaluating large language models, LLM agents.
Right.
But with a crucial focus, diverse real-world video games, not just toy problems.
Okay, let's get into this. We've seen LLMs tackle specific games or tasks before, sure. But the paper argues there were some pretty significant gaps ORAC is trying to fill. What were those core problems they spotted?
Yeah, the authors found that the previous benchmarks just weren't comprehensive enough. Critically, they lacked evaluation across a wide variety of game genres. That was a big one.
Uh-huh.
They also didn't sufficiently probe the crucial agentic modules, things like planning or reflection, the internal bits that help LMs reason and, decide what to do next. And importantly, there wasn't really a robust collection of fine-tuning data sets derived from actual nuanced gameplay to help make these agents better.
So ORAC is stepping in to provide that missing piece, that broad spectrum testing ground. How extensive is it? What are we talking about here?
It's pretty substantial. ORAC pulls in 12 popular video games, and they were deliberately chosen to cover all the major genres you'd think of: action, adventure, RPGs, simulation, strategy, puzzle games.
That kind of variety really means you're testing a completely different set of capabilities depending on the game, right? Give us a few examples just to highlight that range.
Absolutely. So you've got like Street Fighter 3, a classic fast twitch fighting game.
Okay.
Then Super Mario, the iconic platformer, needs precise timing. Minecraft, obviously, that massive open-world sandbox demanding exploration, complex crafting.
Yeah, very different.
Absolutely. Then StarCraft 2, a deep RTS about economy, tactics. Baba Is You, which is a really unique puzzle game where you literally change the rules.
Oh, I know that one. Clever.
Right. Yeah. And even something like 2048, a simpler numerical puzzle.
Yeah.
That whole spectrum really forces the agents to engage different kinds of, intelligence and decision-making.
So the challenge is, how do they actually evaluate these LLM agents consistently across environments that are just so fundamentally different? That sounds like the main technical hurdle here.
That's exactly it.
Mhm.
And that's where ORAC's core technical framework comes in. They built this plug-and-play interface. It's based on what they call the Model Context Protocol, or MCP.
MCP.
Think of MCP as like the standardized communication layer. It lets different LLMs connect pretty seamlessly with these vastly different game environments. And crucially, it also lets them interact with the various agentic modules the researchers want to test, like reflection or planning.
So MCP basically standardizes the input coming from the game and the output going from the LLM, no matter if it's, say, Street Fighter or StarCraft.
Exactly. It abstracts away all those game-specific details for the LLM. The game state, whatever its original format is, gets packaged up and presented to the LLM via MCP. The LLM processes it, maybe uses its agentic modules, decides on an action, and then sends that action back through MCP to the game.
And the data they get out of these interactions, what does that look like, technically speaking?
They generate these really detailed LLM gameplay trajectories.
Yeah.
And these aren't just, screen recordings. They capture the sequence of the LLM's decisions and the state it actually saw at that moment.
Okay.
The format is given as ACALDES SYAI1.
Yeah.
Which basically means for each step, or maybe sequence of steps, where the LLM used a specific agentic module A, it records the prompt given to that module, the game state the LLM received, S, and the LLM's actual response or decision. Yeah.
That level of granularity sounds key. It lets you analyze why the agent did what it did at a specific moment, right? Seeing the input it got and the internal process, the module inference that led to the output.
Precisely. You can see if it maybe misinterpreted the state, or if a specific module like reflection helped it correct a mistake, or if its planning kind of went off the rails.
Makes sense.
And the evaluation components go beyond just a final score. They have leaderboards, yes, but also dedicated LLM battle arenas for the competitive games, and crucially, detailed analyses looking at how the agent interpreted visual state, the specific strategies it tried, and the impact of fine-tuning.
All right, let's jump into the technical specifics for some of these games. Street Fighter 3, that's a great example of a real-time adversarial environment. How'd they set that one up?
So for Street Fighter 3, they use the Diambra Arena environment. It's Docker-based, often used for RL research reinforcement learning.
Right, training agents with rewards.
Yeah. Diambra provides raw game state like health bars, the timer, super meter, that kind of thing.
But fighting is so dependent on positioning, movement. How did they capture the visual state that really matters there?
Good point. The raw state didn't include that nuance, so they added a layer. They ran a YOLO-11 object detection model on the game frame 224 by 384 resolution.
Okay. CV.
Exactly. This model extracted the character positions, calculated their relative distance, and then classified it into simple text categories like very close, close, far. This enriched state, text plus the raw numbers, was fed to the LLM. It's a pretty smart way to use computer vision to turn that visual info into structured text the LLM can actually process.
That makes a lot of sense, abstracting the visual into meaningful text features. What about the actions? Fighting games have complex combos, timing.
Right. So the base Diambra environment offers 18 discrete frame-level actions like move left 1 frame, press light punch. But getting an LLM to control those frame by frame, that's incredibly hard.
Yeah, I can imagine.
So what they did was use a higher-level action space. Semantic commands like move closer, jump, or do a low punch were mapped to predefined sequences of those low-level inputs. This lets the LLM focus more on the strategy what to do rather than the super fine-grained timing details.
What agentic modules did they really put to the test in Street Fighter?
They tested the basic zero-shot agent, just the LLM itself. Then reflection, planning, and a combination. Reflection planning.
And the results? Any technical insights or, surprises from that fast-paced environment?
Yeah, the ablation studies where they turned modules on and off showed some interesting dependencies. For the smaller Llama 3B model, explicitly using the reflection module gave it a clear performance boost.
Interesting.
It suggests that for models maybe with less inherent strategic depth, prompting them to explicitly reassess their previous actions and plan revisions is really beneficial in such a dynamic, reactive game.
So reflection kind of acts as a self-correction mechanism for the less capable models.
Exactly, like reminding itself, okay, charging in didn't work, maybe rethink that. But for the more powerful GPT-4o, both the zero-shot agent and the planning agent performed well on their own. GPT-4o's inherent capabilities seem pretty sufficient, making that explicit reflection less critical for single-player success, at least.
They also looked at whether giving the LLM the raw game image plus the text state helped versus just the text state alone, didn't they?
Right. And for GPT-4o, Gemini, and Claude, the text-only input and the multimodal, the text plus image input, were actually comparable. Or in some cases, text-only was even slightly better. Yeah, the raw image didn't seem to provide significant added value for these models in this specific context.
That feels counterintuitive, doesn't it? You'd think seeing the fight would be crucial.
It does seem that way. But perhaps the abstracted text state, which already included key visual info like relative position for a YOLO-11, was actually sufficient. Adding the raw image data might have just introduced noise or complexity that the model struggled to integrate effectively for, strategic decision-making in a game this fast.
Right.
It really highlights that raw visual input isn't always the best answer if the crucial information can be structured better maybe as text.
And the multi-agent arena fighting games are all about head-to-head. Did the dynamics change much there?
Okay, here's where it gets really interesting, especially for our audience thinking about adversarial systems. In the pairwise battles, just using the basic zero-shot agent, Minitron 8B, which is an open-source model that didn't particularly shine in single player.
Yeah.
It consistently outperformed proprietary models like GPT-4o.
Wow. Seriously, a smaller open-source model beating the big guns in direct competition, that's a significant finding.
It absolutely is.
Yeah.
This result is technically fascinating, and it has strong parallels to adversarial systems, like you said. It really highlights how an agent's behavior and its strategic effectiveness can change dramatically when facing an intelligent, adaptive opponent compared to just a predictable single-player benchmark.
So it suggests maybe emergent behaviors or unique strategies might only pop up in competitive settings.
Exactly. It could reveal strengths or weaknesses you just don't see in isolated testing.
Yeah.
And that's highly relevant when you're thinking about how AI agents might behave in contested digital environments.
That comparison to adversarial systems is spot on. Understanding why Minitron 8B did well there could offer clues about how maybe seemingly weaker systems might exploit dynamics or vulnerabilities that stronger ones overlook when facing a clever adversary.
Precisely. It shifts the evaluation focus from just, can it complete the task, to how does it handle strategic interaction and pressure from an unpredictable opponent.
Okay, let's pivot to Minecraft. Very different game, open-ended, exploration, resource gathering, and critically crafting using complex action sequences.
Right. For Minecraft, they use the MindFlayer JavaScript API. And this means the action space isn't simple button presses or even high-level game commands. It requires the LLM to generate executable JavaScript code.
actual code.
Yes, code for the bot to perform actions like mine block, oak-log, or craft item, to explore until entity, cow.
So the LLM isn't just deciding what to do, it's generating the literal script to do it. That's a much higher bar, technically.
It really is.
Yeah.
And the evaluation was pretty straightforward.
Yeah.
Success rate of crafting specific target items. You check if the item appears in the bot's inventory. But the task involves chaining multiple complex steps, find resources, mine them, manage inventory, use crafting tables, all through generated code.
How did the models actually handle generating functional, executable code in this environment? Did they manage?
Well, the results here were particularly telling about current LLM limitations.
Yeah.
The open source models largely failed to craft anything, like score 0.0.
Zero.
The paper specifically notes that 5 of the 6 open source models tested failed to generate any executable JavaScript code compatible with Mindflayer at all.
Wow. So they just couldn't write working code for that specific API. That's a critical limitation when you think about agents operating in code-dependent systems.
Absolutely. Minitron 8b, interestingly, could generate valid code sometimes, but it still couldn't complete the full crafting sequences to actually make the items.
Okay. What about the proprietary models?
They did better. Models like O3 Mini, Gemini 2.5 Pro, and Claude 3.7 scored around 75.7. They successfully crafted simpler items, but they still failed on more complex targets, like an enchanting table or a nether portal. That indicates limitations in generating those longer, more intricate, or maybe state-dependent code sequences.
What about the agentic modules in Minecraft? Did reflection or planning help with this coding challenge?
Yes, this is where reflection really showed its value again. The reflection module significantly improved GPT-4o's performance.
How did it help with the code?
It basically worked by prompting actions based on feedback from failed attempts, or by observing the environment state after trying an action. So if the code failed, reflection helped to try again, maybe differently.
Ah, iterative refinement.
Exactly. They also noted the importance of a skill management module. This wasn't explicitly tested in ablation, but it involved reusing past successful code snippets, essentially building a library of code that works.
So having a mechanism to learn from code execution failures and reuse successful code was crucial for these complex code-generating tasks. That feels directly relevant to validating AI behavior when they're writing or interacting with code in potentially sensitive systems.
It's a very clear technical demonstration,
Yeah.
It shows the need for explicit mechanisms that let agents debug or refine their outputs when those outputs are functional commands interacting with an external system, whether that's a game API or, something more critical.
Okay, let's move to StarCraft 2. Real-time strategy, giant managing economies, building armies, tactical combat, complex map.
Yeah, StarCraft 2 presents a huge challenge. Long-term planning, resource allocation, reactive tactics, all in a partially observable environment. The environment they used, Bernie-C2 Python C2, provides a raw scripted interface.
What do you mean?
Meaning the state is purely text-based. No graphics were fed to the LLM here.
So the state is described purely in text. Resource counts, unit lists, building progress, research status, info about enemies you've scouted, that kind of thing.
Correct. And the action space is a set of 72 discrete actions. Things like train marine, build barracks, but also strategic operations like attack ground at specific map coordinates.
And evaluation.
In single player, it was simple win rate against a built-in AI. In multiplayer, they used army supply difference as a proxy for who's winning.
How did the models handle this complex, strategic, text-based environment?
In the single-agent play, GPT-4o and Gemini 2.5 Pro again showed really strong performance, 100% win rate against the static AI.
Okay.
The open source models, conversely, really had difficulty mastering the complex build orders and strategic timing needed. They ended up with 0% win rates.
So executing those complex strategic plans and build orders seems to require the kind of higher reasoning capabilities found in the larger proprietary models, at least for now.
That's certainly the implication from the single-player results. Now, in terms of agentic modules, the combination of reflection plus planning was most effective for GPT-4o, also getting that 100% win rate.
Okay, that makes sense. Planning plus checking your work.
Right. But strikingly, reflection alone actually degraded GPT-4o's performance compared to just planning, or even the base zero-shot agent.
Wait, really? Reflection made it worse for GPT-4o in StarCraft? That seems odd.
It is strange. A plausible technical explanation, maybe, is that in the fast-changing state of StarCraft 2, the explicit reflection step, if it wasn't tightly coupled with a strong forward plan, might have led the agent to constantly second-guess itself or make suboptimal reactive adjustments that actually disrupted its overall strategy more than helping it.
Huh. So context and how these modules interact really matters.
It really seems to. And for Llama 3B, none of the agent types, modules or not, improved its 0% win rate.
And modality for StarCraft 2. Did text-only versus multimodal show similar results to Street Fighter?
Yes, and it really reinforced the pattern. For GPT-4o, Gemini, and Claude, using both text and image inputs decreased performance compared to text-only input in StarCraft 2.
Even though the image wasn't the primary state representation, adding it in somehow hurt performance.
Precisely. The paper suggests that for StarCraft 2, the critical information resources, unit counts, tech tree status, it's all better captured and more directly actionable when it's in structured text. Adding the visual map data likely introduced complexity or noise that the LLMs struggled to integrate effectively into their strategic decisions. It might have even distracted them from the crucial text-based state variables.
That's a really strong signal then. Simply dumping more data, especially visual data when the core info is text-based, isn't always beneficial and can sometimes actually degrade performance.
It's a significant technical takeaway, applicable way beyond games. State representation really matters. How you choose to represent the state of a complex system to an AI agent is critical.
Absolutely. Raw multimodal input isn't inherently better if key information is structured elsewhere.
Okay, and the multi-agent arena for StarCraft 2. Did we see those unexpected competitive dynamics again?
We definitely did. In competitive play, Claude surprisingly achieved the highest ELO rating. It performed better than GPT-4o, which had that perfect single-player record.
Claude came out on top. Interesting.
And echoing the Street Fighter results, Minitron 8B, despite its 0% single-player win rate, managed to beat GPT-4o and other theoretically stronger models in some competitive matches.
Okay, so another clear demonstration that single-player benchmarks just don't fully predict adversarial performance.
This is perhaps one of the most crucial insights from ORAC, especially for security folks. Agent behavior, strategic effectiveness, the potential for surprising outcomes, it's all fundamentally different in a dynamic adversarial setting compared to a static or predictable environment.
Right.
It really underscores the need for specific adversarial testing when you're evaluating AI agents for critical applications where they might interact with other intelligent entities or even face deliberate manipulation.
So let's synthesize these findings on the agentic modules and input modalities across these diverse games. What's the big picture?
Well, the core insight seems to be that modules like reflection and planning aren't silver bullets. Their effectiveness is highly context dependent. It varies based on the game type, the task, and the base LLM's own capabilities. They can provide crucial boosts for weaker models or enable complex tasks like we saw with code generation in Minecraft. But for stronger models, or in specific strategic contexts like StarCraft 2, they can be less impactful or even detrimental, depending on exactly how they're implemented and used.
And the consistent finding on input modality, text versus multimodal.
Yeah, across multiple games, they mentioned Ace Attorney, Her Story, Slay the Spire, Darkest Dungeon, in addition to StarCraft 2 and Street Fighter, where we saw it potentially hurt. Text-only input was often sufficient or even superior to multimodal input.
And the technical reason seems to be?
It seems to be that the crucial decision-relevant information, things like character stats, dialogue options, card descriptions, inventory contents, research status, it's just better captured and more easily processed by the LLM when it's already structured nicely in text. Images might add ambiguity or noise for certain tasks.
This paper also mentioned they released a fine-tuning dataset.
Yes, they did. They built a dataset from the gameplay trajectories of the top-performing agents on ORAC. The goal is pretty straightforward. Provide valuable data to researchers to help fine-tune existing pre-trained LLMs, help them learn from successful gameplay strategies, and hopefully become more capable gaming agents over time.
All right, pulling back to the bigger picture then, what does the ORAC benchmark and all these results we've discussed fundamentally tell us about LLM agents operating in complex, dynamic, and potentially adversarial environments, the kind we encounter in domains like digital security?
ORAC provides a really valuable, standardized, rigorous technical lens. It shows us clearly that different tasks and environments require different fundamental LLM capabilities. You need logical deduction for puzzles, sophisticated planning for strategy, rapid state interpretation and action sequencing for real-time games, and even code generation for interactive systems like Minecraft.
And we learned that those reasoning modules and input types have really non-trivial effects. They aren't just simple add-ons.
Exactly. Agentic modules aren't universally beneficial. Their utility depends heavily on the task and the model. And that striking, repeated finding that text-based state representation can be sufficient, or even better than multimodal input, really highlights that how we feed information to these agents is a critical design choice. It can significantly impact their performance and maybe even their robustness.
And most relevantly for UBG Bytes listeners, those findings from the multi-agent arenas.
This is arguably the most important takeaway for understanding AI agents in adversarial contexts, I think. The fact that models performing poorly in single player could actually outperform stronger models in head-to-head competition that demonstrates that adversarial performance is an emergent property. Single-player benchmarks might not predict it at all.
Right.
It really underscores the potential for unexpected strategic interactions, emergent vulnerabilities, maybe even surprising resilience when AI agents are placed in these contested environments.
So understanding how these LLM agents interpret complex states, generate outputs including functional code, and behave under pressure against an intelligent adversary, that provides absolutely vital insights for assessing AI agent behavior in security scenarios. Whether you're analyzing potentially malicious AI or trying to predict vulnerabilities in systems that incorporate AI agents.
It definitely shifts the focus from simply asking, does the agent complete the task, to how does the agent behave when the environment is dynamic and potentially hostile? Can it be tricked? Does it reveal new vulnerabilities when interacting with other agents? Those become the critical questions.
Well, that was a really insightful look into the ORAC benchmark. Thanks for breaking down all those technical details.
My pleasure. It's fascinating stuff.
And thank you for tuning in. Considering everything we've discussed, the complex ways LLM agents interpret states, generate actions including code, and exhibit these surprising strategic capabilities or limitations, especially when facing off against each other in dynamic game environments. What questions should you, as the listener, be asking about the behavior of advanced AI agents operating in real-world, potentially adversarial digital systems? Think about online networks, critical infrastructure, or even how they might behave during red team exercises.
Yeah, it really compels us to think about evaluating not just their function in isolation, but their resilience, their predictability, and their potential for emergent, perhaps exploitable behavior when they're actually part of a larger, contested digital ecosystem.
Definitely a lot to consider. Until next time, stay secure and keep digging.